So last time we were covering these topics, okay, where are we? We covered all the how to read the plan and everything, correct? So one, we left it that, the broadcast hash join. So if you're broadcasting your data, and in one of the previous session, we discussed how do you broadcast, your data, and how do you see whether your data is broadcasted. Even, Spark Optimizer will also broadcast some of your data. If it finds your data set, which you are using is, the size of that is pretty small. So if data is broadcasted, you will see dataset broadcast operator. And if you see that broadcast exchange operator, sorry, if broadcast exchange operator, you see that means data has been broadcasted. It will be available on each executor machine. And the broadcasted data is joined. When it is joined with another data set, you will see broadcast hash join in your plan, and we'll see this example. So it will be a separate job in itself, but when we separate job on the UI, when you go to the Spark UI, you will see, the different jobs. And maybe today we'll cover some part of that UI also. So take this, you have this, it just a random, Spark thing. So you are taking some, range of 1 to 100 as A, you're joining with 1 to 100 as B, where A.id is A.b, right? So basically it just says the random 1 to 100 I'm creating, 1 to 100 I'm creating, I'm joining. That's all it is. So when I print the plan of this, the physical plan, you can see this exchange has happened, a broadcast exchange has happened, and then the broadcast join has happened, right? The join is inner type and everything, correct? So that's one way to see. That's, to see whether your data has been broadcasted or not. So that's about the plan, physical plan, and about broadcast hash join. These are some references. You can go through this. Now what we are going to cover is we are going to cover some data set and some dataset Dataframe operations, which some we covered already, which are commonly used. This, what I'm covering is, it's not commonly used. Some people don't know this, so they might, do some workaround instead of using this, in case they have some problems where you could use this. So one method in dataset class is explode. We use this explode for array, list, and map type of columns. So it explodes array or columns, array or all of this columns to rows. And I'll show you an example. It has many variations. One is explode, just explode. It will ignore null or empty columns, and I will show you. One is explode outer, same as explode, but it will not ignore null or empty columns, but it will turn null. PUS explode, it is same as explode, but create two new columns. One column position to hold the position of the element. Let's say if you're an array, right? Array, integer array, 1, 2, 3, 4, 5. So now explode, and it is, you have a record in your data set. That record has some normal columns, string or integer or something, and then it also has one array column also. So array column is 1, 2, 3, 4, 5. So when you explode, it will split, it will explode that row into 5 rows. Every column value will remain same, except for this array, which has 1, 2, 3, 4, 5. The column value for these rows will be, as we said, 1, 2, 3, 4, 5. And in the position explode, it will add another column called position, which will hold the position of the element, right? And the second column called call will hold the actual array value. Of course, it will ignore the null and empty value. If you use PUS explode outer, it is same as PUS explode, but won't ignore null or empty value, rather will return null. And let's see an example of this. So I have this data set, so same data set I keep using, like this is a data set I have, whatever, you have used this earlier, correct? And at the end of, you see, you saw that I had hobby, cricket, comma, Netflix, comma, walking, or whatever, correct? So I read the data set in CSV format. And then I say, I do some triaging, because I want to convert these hobbies as array. So I use this, I say data.select, whatever all columns I have are good, but split this hobbies column I used comma as a delimiter and convert it to it's an array. And if you print the schema, you will see that last column is an array. So now what I do is I drop the hobbies column, because it was, comma separated list. Then I select everything and explode array. So this is where I'm exploding, the hobbies column. And I say it as the hobbies column I put it as an H array. So I explore that H array because it's a array type, and the the column name is as hobby, and I drop H array. Correct. So now if you see this, a drop H array is nothing but the comma separated list of hobbies as array. So now what this result is that I had in the initial in the data set, I had cricket, comma Netflix, comma walking for each of the for this record, for example. This explored, kept everything same. If you see everything same for first three records, only thing is that hobby got split into multiple rows. So same is the thing with second. It had only one record for two, and with the explode, it got split into multiple records because whatever number of hobbies you had, those number of records it got converted. Now, if you see the last record in this data set which you are reading didn't have any hobby, so that record doesn't appear here because we are using explode. If you use explode outer, you will see last record also appearing. So maybe this is a homework you can go and do. Instead of use this explode, but use explode outer also, and you will see the last record also appearing, the record which doesn't have hobby. I will cover join. So I think most of you come from the SQL background, so you might already know about join. You can go to this Spark reference. It explains about joins with some examples also. But I will cover what are the type of joins we have. One is inner join. If you don't give anything, so then by default it's inner join. I think you all know what inner join is. So you can say select. There are many ways to join. One way to join is whatever from imply inner. Like this is one this thing. This is one data set. Is another data set. You are joining these two on these columns. There is Dataframe.join is also there. You don't have to use this. You can say df.join or dataset.join, and the join operator will ask you the type of join and on which columns you're joining. The join types are right joins. Inner join I already covered. Another one is right join. It has values from the right, matched from the left, or null if no match. So you have when you join, you have left hand side and right hand side. If you do right join, all the records, all the all values from the right, everything will come from the right, matched from the left, or if the records are not matching on the left, then it will come as null. The left join, same, all values from the left, matched from the right, or null if no match. Full join, all values from both relations, left and join. If left has corresponding match on the right side, it will appear on the right. If it doesn't have match on the right side, it will on the right hand appear as null. Same is the case on the right hand side. If it has match on the left hand side, it will appear. If it doesn't have match on the left hand side, it will appear as null. Semi join, values from the left which has match on the right. Anti-join, this not many people know. It values from the left which has no match on the right. So generally join means that you join on the match, but anti-join is with the value on the left which has no match on the right. Of cross join, of course, you all know it's a Cartesian product. There's a sort. So you sort the data frame. It's same as order by. It can be done on one or many columns on ascending or descending order. If you don't give anything, it's by default is ascending. So now see the data set which you're reading, right? This is a data set, and the last record has null. Now what we do is, this is not a good example because generally it's what you do when you have similar records in the same column with some variation. But let's see, this is good enough to give, this example is good enough to explain how different sorts works. So I'm sorting on the name ascending. So you can see, right, in alphabetical order, it's ascending is happening. Then designation descending, there is not much because one person has only one designation. If there are two people having the same designation, you could see that designation is in descending order. The hobbies, ascending nulls first. So same thing here, in the hobbies, the nulls, when you say ascending nulls first, I said, right, you can have ascending order, descending order. You can have normal ascending or descending, or you can say ascending nulls first. So null will come first. So it will get in ascending order, but null will come first. So that's how it is. This example is not a true representation because for this last thing to work, we should have had two multiple people with the same name possibly, then you would have seen it. But at least you get the idea. If you can do you can do sorting on the multiple columns, each column in a different order, ascending or descending, and both ascending and descending have null first also, so that nulls in that column appears first. You have sort within partitions. So what sort within partition does is it sorts within the partitions, as the name itself suggests. It's local ordering, and there's no shuffle involved, right? So that's sort within partitions. There's a union. You want to combine two data sets for data frame, you use union. There's a collected list. It returns a Java list containing all rows in the data set. You have to be careful with this because all these rows will be moved to applications driver JVM. The driver JVM it will move, and it might catch out of memory error. Generally use this for debugging purposes. When you have small data set, you want to test something and you want to print on the driver. One possible reason of using this is could be this use case, but generally in production you don't use if the data set is used, you don't use this method. Count, it runs number of rows in the data set as the count of the SQL does. Where it filters, it's same as filter and where are same. Filter rows based upon given condition, it alias or filter. So both are same. People filter who has age greater than 15, or filter where age is greater than 15. So filter and where both are same, right? If this condition is passed, then only the output, those will be part of the output data set or data frame. Persistent cache, this is important. It stores the intermediate computation of RDD data frame or data set. You should use this when you have multiple actions. If you have only one action, generally, you don't, there's no point in using this. If you see, we talked about the lineage of data sets. Lineages, you read from some data set, read some record from data set using Spark and created a data frame out of it. Then you applied some filter, then you applied some aggregate, then you saved into a database, and then you're saving that again into some other file also. So if you now saving to database, saving to another file are two different actions. If you don't persist or cache, what will happen is your first action, which is saving to database, will trigger the DAG from beginning till end. And the second action, which is saving to a file, will again trigger all the transformations from beginning till end. So if you want to avoid, because your first action has triggered all the transformations, and second action should not be triggering all the transformation because first action has already done it. So preferably you save this, you persist or cache this, so that your you get benefit in the performance. So RDD also is a cache method. So their cache is memory only storage. Dataset class also is cache method. It's memory and disk. You can specify by default it's memory and disk. The cache method of dataset data frame internally calls persist, and which caches the result. Persist is fault tolerant. If the node goes down, it gets computed. So we should use either dataframe.persist or dataframe.cache. Unpersist is if you want, when you are done with your program, you don't want to keep that persistence of whatever data set you have persisted. You don't want to have that anymore. You can use dataframe.unpersist. I think there is one thing in these memory only and memory and disk. There's a disk only. These are the storage levels which you can pass during your while you are invoking these methods. So it will save those that information accordingly in those storages. This encoder, I have an encoder example in coming slides also, but it converts a Java object to and from internal Spark SQL implementation. When it's a Java object, consider this a Scala object also, because Scala ultimately gets converted to Java object only. In reality, it's a raw converter. So you have this imports Spark implicit. This you do after creating Spark session. If you don't, if you do this before creating Spark session, then it won't be effective. So once you created a Spark session in your code, then you import Spark implicits. Then only thing I'm doing is that, sequence 1, 2, 3 to DS, it just, it just converts into, by default it detects it's a int, and it converts into data set of type integer. You can see more details here. That person has given good examples how this encoder internally works. But I have copied some examples in the coming slides. We'll discuss about tempViews. What are tempViews? I think I have example of tempViews here. So we'll go through the example of this thing. So tempView generally you create when you are reading data from some data sets, and you do something and with the data sets. Now you want to create some tempView with some given name, and you want to do some operations over that view. So as the name suggested, it's a view only. And when if for when you use create tempView, by the way, most important thing is not tied to any database or any file or anything, because it might so happen you might have read data from some file, and you might have broadcasted some data, you might have joined this data, and based on certain column this joined data, you're getting some tempView. And that tempView you want to apply, you want to query something or do some aggregation over the tempView. And once you are done, then you don't want, once your program is over, you don't want to do anything with the tempView, it will automatically get destroyed. So this is important. Its lifetime is tied to the Spark session which created this. This is a create or replace tempView. It is same. If you use create tempView, if the create temp, and you have to pass a name. If tempView already exists, then this method will give error. But if you use create or replace tempView, if method already exists, then it will get replaced. If that view already exists, then this method will replace that view. And this is also tied to the Spark session which created this. There's a create global tempView. It creates a tempView with the given name. Now here's a difference. Its lifetime is tied to the Spark application which created this. Here it was for the Spark session. One application can have multiple Spark session also. So if you create a tempView with Spark session, and you can't access that, let's say you have two sessions, session 1 and session 2 in your Spark application, and you create a tempView with Spark session, tempView 1 with Spark session 1, you can't access this in Spark session 2. You can access only within the Spark session 1. But if you create global tempView, then you can access across sessions. It's same, if create or replace global tempView, it will replace if the tempView exists. If you issue this command and the global tempView exists, it will error out. Now, in which scenarios, question is in which scenarios will need more than one Spark session? Well, Spark sessions, as you said, right? You have your data sets, you have your broadcast variable there, and of course views isolated. You can have those isolated in Spark sessions. Generally, I don't know when you might need multiple Spark sessions. Maybe some scenarios where possibly you are using some library to create some session, and that library is connecting to some data sets which is confidential in nature, which you don't have access to directly, and that library will give you some session for that data sets. And second session you want to create for your own data sets, because you want to have your own data sets and join with some data sets which are confidential in nature. That's why one possible use case is this. There might be many similar use cases. I have not encountered actually many use cases where you create more than one Spark session, but because Spark gives you this ability, so based on your business cases, you can have multiple Spark sessions. One I already explained, but there might be more also. Yeah, the key thing to remember is that one Spark session isolates things to itself. For example, broadcast join and couple, of course, this views and a couple of other things. I think in one of the previous sessions we discussed that. So if you don't want this to be shared across sessions, then you create multiple Spark sessions. We'll take some example. One example is, let's take one, create tempView. So the same data I'm using, which we use in assignment also, and then what I do is I load this Spark data. Okay, what is this? Some printing error. Then and for this data only, I'm creating or replacing a tempView. I call this employee. Now, one advantage of that is now I have created this as an employee. I can run any SQL over this. I can say select star from EMP, which is the same name here, where salary is greater than this. So it gives me that. Or any other SQL which you can think of, you can run over this EMP, because it's a view and it allows any SQL to be run. So that's tempViews. I think what you can do is you can practice on your own how to create global temp view with multiple Spark sessions, and try to access that view created from one session, try to access it from another session and see if it is accessible or not. So that's about tempViews. We'll cover some of the schema for dataset. I think more or less we know. It might be just a revision, but let's still go through this. And this is a good example of this link explains some good example of that. So I have two rows with the name and age possibly, and this is just a row. And then this, I think here, I don't know why I have this slide. This is a 2-row schema for DS. It doesn't have, it's just a row. What I try to explain is that once you create this row, this just has a row, and row, it's a data frame, like it's RDD of type row. A row doesn't have any schema as such of its own, right? So what I have tried to do is here is you have a data frame, similar thing, but I have created hello world and something and something. So I'll say here I'm passing the schema and the column names. I'm saying label and sentence, and these are column names. So when I print the schema, it says label and sentence. Of course, it automatically detects I am not putting this under double quotes, so it becomes integer. This is under double quotes, so it becomes a string. So if I if I say if I want to know the schema of one particular column, I can say df.schema, the column name and the data type. It gives me that it's an integer type. You could, we'll see some examples. You could specify the the column types also. Along with column names, you could specify the column types also. We'll see the in further examples. And how do you do that? Using struct type. I think more or less you all know. So we'll just go through this quickly. For struct type, you import these, you use these two import statements. The struct type, a construct of a constructor which takes sequence of struct fields, which is nothing but collection of struct fields. We'll see some example of this now here. So you can create a new struct type, and you can add, like this also, like because it's sequence, you can add first sequence, which is the column name and the column type, another column name, another column type, right? And when you so this is schema type, and when you create another, this is untyped and this is typed, and I'm saying schema untyped equal to type true, because both have, whether I use int or integer type, whether I use string or string type, both are same. So when I say schema type equal to whether this is equal to this, it returns true, because one way to create this is this, another way to create it, this is this. So either way you can use. You can see the schema. You can say print testing. This is not the data frame. Remember, this is struct type. If you want to see the schema of struct type, you can say print string. It will print like this, or you can say print ln and schema type the petty JSON. It will print in JSON format also. Okay. We are not passing any metadata or any nullable. That's why nullable is coming as true and metadata is coming as blank. We are passing just the name and the type. So that's the schema. Struct field. This is about the struct type. Now, but let's go to the struct field. Struct field, a field inside the struct type. It can create struct type with the following information. So a struct field can have name, data type. Name is mandatory. Data type is mandatory. Nullable, it's optional. It's true by default unless you change it to false. Metadata, it will be empty by by default, and you can add some value if you want. So I'm creating this struct field. Name, ID, data type, long type, nullable, false, and some metadata. I think I'm just leaving it blank, metadata blank. And this is one. You can also nullable. You can also pass nullable equal to true. If you pass nullable equal to false, and you assign this struct will be part of some struct type, and you assign the struct type to some data frame or data set. If that data set has this column, because ID is nullable is equal to false. If you assign this to some data set, if data set has ID column as null, then it will throw error. It will just throw exception and it will fail. Here I'm passing nullable is equal to true. How to convert data frame to dataset? Simplicity. Okay, so you have a data frame. This data frame you have, and I'm passing this name and age. This is a sequence and converting to data frame, and column names are name and age. I'm creating a class person which has name and age. Name is string, age is int. I import Spark implicits, and that's all I do. I say data frame dot as person. It automatically converts this, because this each record here can map to this class without any issue. So I can convert this data frame to dataset like this. This we already covered, but I'll just repeat it one more time. So you can apply expression to dataset and data frame. Like one expression, I have sum of salary. I create this data frame, name and salary, and then I create an employee class, name and salary, import Spark implicits. Then I do data frame to dataset conversion using data frame dot as employee, because implicits are there, it automatically gets converted. And now I say dataset dot select expression. You see select expr. Then I pass this expression, and this expression is nothing but sum of salary. So it will give me sum of salary, and I say this s dot show. It will give me sum of salary. This is another way if you want to get some aggregates from some data set or data expression. Windowing function we'll cover next time, because I have to add some examples also. Let me go to the next slide. I thought I had it here. Slide number 4. I will cover the UI. This Spark UI. If you get, I don't think we'll get time today. But I want to cover the Spark memory. So next time we'll start with Spark UI and the Windows function. So let me start with the Spark memory. I think someone had this question, someone had this request to go through the Spark memory. So Spark memory consists of 2 memories. One is the driver memory. We know what driver is, right? So driver memory is part of the JVM memory only. Then you have executor memory. You have execute, let's say you have 100 node cluster or 1000 node cluster. Executors are running on all 1000 nodes, for example. So executor memory will be on all 1000 nodes. On executor, you can, because executors are running in the JVM only. So you can access on heap memory, you can access off heap memory also. So I don't know how many of you have gone through the LinkedIn article I published for using the off heap memory. If you have not gone through, just please go through that. There I've explained I have written a complete Spark program, how to use off heap memory and how to validate you are using off heap memory through Spark UI. So go through that. But here idea is that executors can access off heap memory. But what is off heap memory? Memory which is outside the JVM. So JVM memory is on heap, which is outside the JVM, which is an operating system. So that memory also you can access using Spark. Now we'll go through some setting, and this is a configuration of Spark. You can go through this. I have tried to explain you the box. This is a total memory we have. Out of total memory, around there is some reserved memory, and that reserved memory is around is fixed. It's around 300 MB or something. This is used for some housekeeping or for something which operating system will handle for Spark. So we can't access this memory. So it is out there. The total memory available is the heap space minus 300 MB, right? So so this is our total memory. When I say this is a heap memory, I'm not talking about off heap memory at this moment. So this is the total memory. Now 60% of the total memory, in the total memory, you don't include this. So whatever you have left from here, whatever you have left from here till here, 60% of that is reserved for storage and execution. So storage and execution is by default, there's a setting called, there's a configuration called spark.memory.fraction. It is 0.6. If you don't change it, then this is 60% of the total memory. It is reserved for storage and execution. What do you mean by storage and execution? We discussed that, right? For example, you can persist or cache your data set or data frame. You have broadcast variables. You will have variables inside your Spark program also, right? So this memory gets used for that, 60% of that. I've given an example. Let's say I have 32.3 GB memory. So 60% of 32.3 GB memory is 19.2 GB. So that's your memory which is used for storage and execution. Then within storage and execution, you have some memory for storage fraction, and you have memory, you have some memory available for storage, and you have some memory available for execution. Now, here's a trick. Generally 50% is available, correct? So out of 19.2, 50% is 9.6, which is available for storage. When you say storage, where we use Persist And Cache, that's storage. Execution, your all the variables, broadcasted data and everything is part of this memory section. So now amount of storage memory is immune to eviction. So you cannot change whatever storage memory you have. It is immune to eviction. It is expressed as a fraction of the size of region set aside by spark.memory.fraction. So if you see spark.memory.fraction is 50% and spark.memory.storage fraction is also 50%, both should come to 100%. And that is part of this 60% within this 60%. Now, I will explain you in detail what we mean by immune to eviction in the next slide. But I hope this is clear. So I'll just repeat. Of the total memory available, 300 MB is reserved. That you can't touch. Spark can never touch. Out of whatever else is available from this, except this 300, 60% is reserved for storage and execution. Within 60%, you have memory reserved for storage, which is controlled by this. Memory reserved for execution. If by default, if you don't change anything, it is 5%. So 50% of this will be available for storage. 50% for this will be available for execution. Now storage memory. So it is used for caching, broadcasting data. Actually, storage memory, broadcasting data is used in the storage memory. My mistake. I said it is used for execution, but it goes in storage memory. RDD, data frame, and dataset are stored here based on storage policies. We discussed it, right? Disk only, disk and memory and everything. Generally 30% as seen from the diagram. So if you consider this 60% and 50% of 60%, right? How much it comes to for the total? It comes to around 30%. So that's what it means. Execution memory, which is your this memory, execution memory. This is used to store temporary data in shuffle, join, sort aggregations. For these operations to complete, there's an intermediate stage to store data, and that's where execution memory is used. You can see the memory management section in this Spark documentation. Now there is one thing: storage and execution memory borrowing. What does that mean? Storage can borrow execution memory. So if storage becomes huge and execution has free memory, it can borrow. Execution can also borrow storage memory. If execution needs memory and storage memory is free, it can borrow. But there are certain rules. What are those rules? Storage can borrow execution memory until execution claims its space. Storage has borrowed its execution memory, but now your Spark program is running. And as we said, right, during execution, we are doing shuffle, join, sort executions. Your Spark program has invoked one or more of these operations. Now it needs memory, but storage has claimed that memory which was available for execution. And in the sort, sort is getting executed. Then Spark will reclaim that memory from storage. It will evict storage from there and reclaim that for execution, because your program should not stop. It needs that memory. So it can tell storage to release that memory for its own use. Now when execution memory reclaims its space, cached storage blocks will evict the memory. It can go to disk, for example. It will evict it, because now we have reserved storage fraction for this for the caching and or persisting, but it has claimed some part of this memory. But now execution needs this memory, so it will tell to release this memory. And if the cache or persist can't fit in the memory which was available to it, it will go out of the memory. It will possibly get returned into the to the disk, unless we have off-if enabled. So we'll talk about off-if later. So if execution can borrow free memory from storage, but storage can never claim back. See, when execution takes more data, it has more data, and it has borrowed some memory of the storage, and storage increases, so storage can never claim back. If storage memory is full, then new storage block will be immediately evicted as per the storage policy. The storage policy is disk only or off heap, whatever storage policy you say, it will go into that. So rule of the thumb is execution takes priority. If storage and each one can borrow, if storage borrows execution memory and execution needs it, execution will tell storage to release it and storage will get evicted. If execution has taken storage memory, then storage cannot take it back. So rule of the thumb is execution memory takes the priority. I have the Spark code, so I've taken some of these things from the Spark code only. So executor memory, there's a unified memory manager .scala that is responsible for this. So I think I have a couple of more slides. I will stop it here. I will not cover the reserved memory, or I'll cover reserved memory and user memory, and I'll stop it here. Off-heap memory will cover next time. So let's go through these 3 slides very quickly. So I will just read it out. This is a documentation from unified memory manager.scala. So this is just repetition of what I just said actually. So a memory manager that enforces a soft boundary between execution and storage. We discussed that such that either side can borrow memory from each other. The region shared between execution and storage is a fraction of total heap space minus 300 MB, because 300 MB is always reserved. It is configurable through Spark memory fraction default 0.6. It's just the box which I showed you. The position of the boundary within this space, within this 0.6 space, is further determined by Spark memory storage fraction, which is by default. This means the size of the storage region is 0.6 multiplied by 0.5, which is 0.3, 30% of the heap space by default. So I'll just reiterate so that you understand. This is the 60% of the memory, and out of the 60%, 50% is available to this, 50% is available to this. This is the storage fraction, right? So this is what it says. This is storage fraction. This is the memory fraction, 0.6. This 60% is the memory fraction. Memory fraction, I think we covered the memory fraction here. This is the memory fraction tells about this 60%, and within this 60%, within the 60%, storage fraction tells what storage can claim and what execution can claim. Storage can borrow as much execution memory as is free until execution reclaims its space. When this happens, cache block will be evicted from memory until sufficient borrowed memory is released to satisfy the execution memory request. Similarly, execution can borrow as much storage memory as is free. However, execution memory is never evicted by storage. The same thing I said, storage memory is the highest priority due to the complexity involved in implementing this. The implication is that attempts to cache block may fail if execution has already eaten up most of the storage space, in which case new blocks will be evicted immediately according to the respective storage levels. So this is what it is, right? The unified memory manager. Reserved memory is 300 MB. It is used for non-storage, non-execution purpose. For example, memory for system or something, right? So in the unified memory manager only you see reserved memory. They have reserved memory in bytes. They have given like this 300 MB, then this KB, then this is byte, right? User memory, whatever is left. So 300 MB is used for this. 60% is used for storage and execution. We know the borrowing rules also. Whatever is less is 40%, approximately minus 300 MB, of course. So it's approximately 40%, which is called user memory. This is a heap space left after reserved storage and execution memory is user memory. Users' own data structures used in transformations are stored here. Spark does not do any accounting for this. So if you're doing some transformation, if you're doing some map operation, within that map operation, you have created some variable or something, or some object or something that resides in this user memory. And Spark has no role to play there because it's up to you. Spark does not know when you will need it, when you will not need it. So when it's normally garbage collection kicks in once your map operation is over and that object is no longer needed, it will automatically get garbage collected through the JVM. So Spark doesn't do any accounting for this itself. I'm just thinking how many of we have. Let's finish off if there are only 3 slides. You read my LinkedIn article because I have explained with the snapshot with the screenshots also. So off-heap is basically the memory which is outside heap. So you see examples here, right? This is all heap memory. But if you want to save your data set or data frame outside this JVM memory, then use off-heap. And you can set the off-heap size in bytes. So in Spark shell, I have set this configuration spark.memory.offheap.size in this many bytes. And I have to enable offheap to by default, it is false. I have to enable it to true. So these are the two Spark configs. I have used this configs in the Spark shell, but you could use this config when you start your Spark program, which is in a jar file or in Python file also. So using Spark submit command also. So you can say Spark submit, and you can pass this conf file, this configurations, enable the heap, and then give this heap size, of heap size. If you don't give any, if you don't enable it and give only this, it will fail. So now let's see the example of this. So same data set I'm using. So here I am importing the storage, and I'm passing, see here, the data dot persist, and I'm saying storage level dot off heap, and I say data dot show. Now how would I know it is off heap? So when I go to the Spark UI, and the Spark UI, you will see storage section here. I click on the storage section, you will see this memory off heap. It is outside the heap, and so that's how I know it is using off heap. And how to open this Spark UI will cover in the next session. But when you start your Spark program through Spark shell also, it will give you URL of UI. When you run the Spark submit, that time also it will give you URL of UI. So that's how I see the off heap memory is used. So I'll stop it here. Now what I want to do is I want to stop the recording.